Hello, this time we're going to get into the geometric elements of the Gram-Schmidt orthogonalization process. And to that, we're going to start with an example of three linearly independent vectors in a Euclidean space. And we're going to explore what are the algebraic and the geometric considerations as we initiate this process. And, well, we're going to do some checking as well as we progress. So I'll start like this. First, I'm going to set W1 to be U1. And from here, what I'm going to get is a picture. The picture goes as follows. This would be the vector W1. And, well, I consider this element already processed. So I have to move to this one. And I want to see what is the new element in the set that I have to construct that is orthogonal to W1, but still has the same spanning set as U1 and U2. So, to do that, well, geometrically, it kind of looks like this. I have U2 here, then I form the projection, right? And the height of this triangle is in a 90-degree angle with respect to the projection, which I'm going to denote here. This would be the projection of the vector U2 onto W1. So, well, what would happen with this? Well, look, I'm going to put some labels and I'm going to call this H1. And from here, I'm going to get the following algebraic equation, which says that H1 plus the projection of W1 U2 results in U2. We can just follow the triangles associated here, right? And, well, what is this saying? Well, this is saying that H1 may be written as U2 minus projection W1 U2, which we can specify algebraically as U2 minus W1 transpose U2 over W1 transpose W1 W1. Now, I'm going to set W1 to be exactly this vector, this H1, which would be U2 minus W1 transpose U2 over W1 transpose W1 W1. And now what I'm going to do is to check that indeed this vector W2 is orthogonal to W1. And to do that, I'm going to multiply it on the left by the transpose of W1. So to get something like this. Note that W1 transpose W2 is W1 transpose U2 minus W1 transpose U2 over W1 transpose W1, W1 transpose W1. Why is this? Well, it's associated with the commutativity of a scalar multiplication with matrix multiplication, right? We can move them across. So with this, well, look, we perform some cancellation. We know that W1 is different from 0, so its norm square is different from 0. So this cancels. This is leaving us with simply W1 transpose U2 minus W1 transpose U2, which is indeed 0, indicating that W1 and W2 are orthogonal. We can check also by kind of a technical manipulation that indeed W1 and W2 span exactly the same vector space as U2 and U1. So now we'll proceed with the next one, right? Which is essentially based on an extension of this idea. So I'm going to set the following picture. Now I have something that looks like this. I have on one side, I have W2, and on the other, I have W1. They form a 90-degree angle as they're orthogonal. And along this one, well, I'm going to form or attach U3. Then what I'm going to do is form a linear combination, but of the projections. This one being the projection of U3 onto W2. This one being the projection of of U3 onto W1. And from this ones, I'm going to form a sum, right? Following the parallelogram law. So this would be the sum of these two, right? This one that I'm writing here is nothing else but the projection of U3 onto W1 plus the projection of U3 onto W2. Now, this turns into a picture that resembles essentially the one that we have right here. So what I'm going to write and produce, and in fact, this has to be in a 90-degree angle because we're projecting onto a plane. So we have the following. We may consider this as the sum of these two vectors, and then here just U3. This one corresponding to the height of this triangle. Here is the 90-degree angle. And, well, now, something that we see immediately is the following. That we can have that if I set this H2 as the height and I move it along these lines, right, I'm going to indicate that H2 plus the projection W1 U3 plus the projection of U3 on W2 is equal to U3. This is something that is fundamental, right? Otherwise, this won't work. And, well, let's take a look. Note that H2 is decomposed in the following way. Is 1 times U3 minus W1 transpose U3 over W1 transpose W1 W1 minus W2 transpose U3 over W2 transpose times W2 W2. Now, what I really want to check is that H2 is orthogonal to both W1 and W2, and we'll do it. So, what I'm going to do is multiply H2 on the left by the transpose of W1 and W2 respectively. So I have W1 transpose times H2 is going to be W1 transpose U3 minus W1 transpose U3 over W1 transpose W1, W1 transpose W1 minus W2 transpose U3 over W2 transpose W2, W1 transpose W2. Now, we have to be careful here because what we observe is that these two vectors are already orthogonal, right? Based on the construction that we did just right here. So these two doesn't really matter what these ones are. We can easily check that this becomes 0. And now, well, we proceed to some cancellation. These are just numbers, right? This goes to 0. This one cancels each other, right? And we're left with the W1 transpose U3 minus W1 transpose U3, which is exactly 0. So this says that W1 is orthogonal to H2. Now to check that W2 transpose, or that W2 is also orthogonal to H2, we have to verify that this product results into 0. And to do that, well, we have this. This becomes W1 transpose, W2 transpose, I'm sorry, U3 minus W1 transpose U3 over W1 transpose W1 times W2 transpose W1 minus W2 transpose U3 over W2 transpose W2, W2 transpose W2. Okay, now this time, this element is the one that goes to 0, right? As W1 and W2 are orthogonal. And, well, what remains is to check that since W1, since W2 is different from 0, this is different from 0, so these two cancel, right? So what remains is simply W2 transpose U3 minus W2 transpose U3, which of course is 0. So with this, we can check that H2 is a vector that is orthogonal to both W1 and W2. And in fact, we can see that H2 is a linear combination of W1 and W2 and W3, and U3. So, what this says, after some algebraic manipulation, is that the spanning set of U1, U2, and U3 is exactly the same as the spanning set of W1, W2, and H2. So H2 is our candidate for W3. And also, we have that the span of U1, U2, and U3 is the same as the span of W1, W2, and W3. Okay, with this let me stop. This is kind of the geometric picture that I want to show. And in a subsequent video, we'll have a full application of this method. I hope that you like it. Take care.